Hello and welcome to Physics Teacher. In this video, I'm going to be going over 5 questions from the equilibrium unit for grade 12 chemistry. Now, if you wanted to skip to any question, you can do so in the time bar. Alright, so let's start with our first question. Here we have initially 1.4 moles of hydrogen and 2.6 moles of iodine are injected into a 5-liter flask and allowed to react at a certain temperature. That certain temperature is important because that just lets us know that our equilibrium point is not changing. At equilibrium, the concentration of hydrogen iodide is determined to be 0.30 moles per liter. Calculate the equilibrium constant for this reaction. Alright, so we need to know the reaction. Let's write out the reaction first. So we're going to have hydrogen gas and iodine gas. Oop, forgot the G. There we go. And that's going to be in equilibrium with hydrogen iodide, also a gas. Then balance your equation. Next, what we're going to do is we're going to write one of our ice charts. So ice charts looks at the concentrations, the initial concentrations, what has changed in order to reach equilibrium concentrations. Now, something else we have to look at that a lot of students make this mistake is check your units. Here they're telling us a concentration. Here they are not. Okay, same with here. So our initial concentrations of hydrogen iodide are actually not given. We're going to have to figure out what they are. Concentration, this is from grade 11, is moles per volume. So we start with 1.4 moles of hydrogen. So for hydrogen, we can just do this on the side here. So 1.4 moles. And it's put into a volume of 5 liters. So we're going to divide that by 5 liters. Okay, and for hydrogen, this is our concentration for hydrogen. We get a concentration of 0.28 moles per liter. So that's our initial concentration of hydrogen. That's what we start off with. So 0.28 moles per liter. Okay, next we need to figure out the initial concentration of iodine. So let's do the same thing here, just on the side. Oops, square brackets. Okay, so we got 2.6 moles. And as well, it's inside our 5-liter flask. When we do that, we get a concentration of 0.52 moles per liter. So 0.52. Now that's what's put into the flask. So hydrogen iodide is not put into the flask. So initially we have a concentration of 0. I'm just going to put a dash through it to represent nothing. Okay, but it does tell us that at equilibrium, the concentration of hydrogen iodide becomes 0.3. So all the way over here, we know what it is at equilibrium at 0.3. So how did it go from 0 to 0.3? Well, we clearly needed to add 0.3. Now, if hydrogen iodide increased by 0.3, look at the mole ratios. This is a 2 to 1 and 1 ratio. So if hydrogen iodide increased by 0.3 at a 2 to 1 ratio, hydrogen and iodide each will have had to decrease by half that amount, 0.15. So if we look at our equilibrium concentrations, we just subtract these values here. And for hydrogen, we get an equilibrium concentration of 0.13. And for iodine, a 0.37. So now that we know all of our equilibrium concentrations, we can write out our equilibrium law. So this is what we're trying to find, our equilibrium constant. And it equals the concentration of our products, so we have hydrogen iodide, divided by the concentration of our reactants, so both hydrogen and iodide. And then look at your coefficients. So hydrogen and iodine are both 1, whereas hydrogen iodide is 2. So we're going to put a square on that concentration. All right, so there's our equilibrium law. And we know all these equilibrium concentrations, so let's just plug them in and figure out what our constant is. So the first one is 0.3. And don't forget to square. And then we have 0.13 times 0.37. So we get, therefore, our equilibrium constant to be 1.9. All right, let's look at our second question. This is a two-part question, so we'll start with part A. Consider the following equilibrium reactions. So we have hydrogen and carbon dioxide in equilibrium with water and carbon monoxide. And they give us the equilibrium constant for this reaction. Determine the equilibrium concentration of each participant, so of everything there, after 3 moles of hydrogen and 3 moles of carbon dioxide are injected into a 10-liter container and allowed to react at a certain temperature. So let's start with our ice chart. So we have our concentrations for I, C, change, and E, equilibrium. And let me just rewrite the equation so we can follow along with which concentrations we're dealing with. So we have hydrogen, carbon dioxide, with water, and carbon monoxide. All right, so the initial concentration of hydrogens, again, be careful, they don't give you concentrations, but you have to calculate it. So just as before, so for hydrogen, it's 3 moles. For carbon dioxide, it's also 3 moles, so we only have to do this once. So our concentration will be moles, so 3 divided by 10, that's 0.3. So we have concentrations of 0.3 initially for both hydrogen and carbon dioxide. And we don't start off with any of our products. Now we don't know the change, but we know all the mole ratios, right? It's 1, 1, 1, 1. It's just simple there. So whatever hydrogen increases by will be the same that carbon monoxide increases by. So let's call that an increase in some unknown value x. And that'll be what our reactants each decrease by. So it'll look like this. So our equilibrium concentrations, we just subtract. So 0.3 minus x for hydrogen. The exact same thing for carbon dioxide. And this is 0 plus x, so we just get x and x for both our products. Now we want to write our equilibrium law. So Ke, which we know it's given to us right here, is going to equal. So start with the product of our products, the product of our concentrations of our products. So we have water times by the concentration of carbon monoxide. Both will be to the exponent of 1. Everything will be to the exponent of 1 in this example, because all of our moles are 1. And divide by our reactants. So we have hydrogen and carbon dioxide. Okay, so we can sub in everything. So Ke is 0.25. And then these two are the same. They're this x, and x times x will give us x squared. And on the denominator, they are also the same, right? 0.3 minus x and 0.3 minus x. So I can just write 0.3 minus x squared. Now it's lucky I can do that because I can avoid a quadratic here, because what I'm just going to do then is square root both sides of the equation. So when I do that, square root of 0.25 is just 0.5. And on the right side, square root of x squared is x. And similarly below, I can just get rid of the square as well. So 0.3 minus x. Now we're going to solve. So 0.5. So just bring this out, multiply both sides by that bracket. And then we can distribute. So we get 0.5 0.15 minus half an x is equal to x, my x. Then add half an x to both sides. So we get 0. Running out of room, but I can do this, equals x plus 0.5x is 1.5x. Okay, let me continue this over here. So divide both sides by 1.5 and we get x equals 0.15 divided by 1.5, which is 0.1. So what are all of our final concentrations? Well, for hydrogen, 0.3 minus 0.1, that's 0.2 moles per liter, which will be the same for carbon dioxide. And for water and carbon monoxide, we have 0.1 moles per liter for both. All right, so let's look at part B. Part B now says, will a net reaction occur with the concentrations given below? Now, I think immediately we can look at that and say, yes, it will occur because those concentrations are not the equilibrium concentrations we just solved for. But let's pretend we didn't do part A and we didn't solve for these concentrations. Let's figure this out. So to figure it out, we already wrote our equilibrium law on the previous questions. Let me just rewrite that. So we have the concentrations of our products divided by the concentrations of our reactants to their exponent of their mole ratios, but they're all 1. So there we go, hydrogen and CO2. Now what we're going to do is something called a trial quotient. So we're going to plug in the concentrations that they give us and see what this trial quotient ends up being. So water, they say, is 0.28. Carbon monoxide, 0.21. We're going to divide that by hydrogen, 0.18. And carbon dioxide, 0.12. We plug this into our calculators, we get 2.7. Okay, well, let's look at Ke. Ke is not 2.7. So definitely, yes, a net reaction will occur. And since this value for Q is actually greater than the value for Ke, we're actually going to get a reverse reaction. If Q was less than Ke, we would have got a forward reaction. All right, in our next problem, we need to calculate the concentrations of silver and carbonate ions in a saturated solution of silver carbonate at 25 degrees. All right, so let's write our equation for this. So silver and carbonate, that's charge of 2 minus, so we're going to need 2 silvers. Right, that is a solid. And we're going to write an equilibrium with our ions. So Ag and aqueous, and same with CO3. And then always double check to make sure your equation is balanced. It is not. We need a 2. All right, now we're good to go. We can write our solubility product using our equilibrium law. And that is going to be Ag. We're going to have to square that, right, because of our mole ratio there, and times that by carbonate. Okay. Next, the KSP value you can look up on a table, solubility tables, right? And you'll find that the KSP for silver carbonate is 8.5 times 10 to the negative 12. Now for silver, the change in silver because of this 2 here will be 2x. And we of course need to then square it. Yes, I get students asking me this question, does that molar ratio mean a 2 for 2x and a squared? It's like, yes, it does. Okay. And then carbonate, just a 1 in front, so a change in x. Okay, now when we square this, that's going to be 4x squared, and we still need to multiply by x, so that gives us 4x cubed, all still equal to our solubility product constant. Next, divide by 4, because we want to solve for x, and since it's x cubed, we're going to want to take our cubic root of both sides, and that will help us solve for x. So when we do that, we get x equal to 1.3 times 10 to the minus 4 moles per liter. So what the question said, calculate the concentrations of these ions in a saturated solution. Well, the concentrations for silver is 2x, that's our equilibrium concentration. If we were thinking about our ice chart, it's 2x. So it's 2 times this, so that would be 2.6 times 10 to the minus 4 moles per liter. And for carbonate, that's just 1 times x, or just x. So that's 1.3 times 10 to the minus 4 moles per liter. All right, the next question is a great one. I love these types of questions. Will a precipitate form? Okay, so will a precipitate form if 125 milliliters of some concentration of iron chloride, iron 3 chloride, is mixed with 425 milliliters of some other concentration of sodium hydroxide at 25 degrees? Justify your answer with appropriate calculation. So don't just say yes or no. We need to figure this out properly. So let's start writing the equation. So let's look at iron chloride. So in this equation, you can see we're obviously using iron 3. So I'm just going to draw sort of a little beaker. So imagine this beaker, and we have some solution, and in it we have ions of iron, we have ions of chlorine, we have ions of sodium, and we have ions of hydroxide. And they're all just floating around. Which combination could actually create a precipitate? Now, obviously, you're not going to combine the two metals. You can't do that. Sodium hydroxide, no, that does not create a precipitate. Okay. Sodium chloride, nope, that is also very soluble in water. It does not create a precipitate. Okay. What about iron chloride? That is also soluble in water. It does not create a precipitate. Iron hydroxide, this actually does create a precipitate. So how do I know this? You have to check your solubility table. So here's an example of a solubility table. You can look these up online anywhere. And you'll notice things like sodium chloride. So if you look at chlorine, chlorine is highly soluble with almost everything except these ones. So I don't see sodium here. So that means sodium chloride is highly soluble. It's going to be an aqueous state. Okay, well, what about chlorine with iron? Same thing. I don't see iron over here. So let's look at hydroxide. Here's hydroxide. Hydroxide's highly soluble with everything in group 1. That's sodium. But I don't see iron here. Therefore, iron is over here, where it's low solubility. That will be our precipitate if we're going to get one. So now that we've identified what the precipitate could be, let's go back and write an equilibrium equation for that. So it's going to be iron hydroxide. That'll be our precipitate. So iron hydroxide, OH, we'll need 3 of them, as our precipitate. And that'll be in equilibrium with its ions, with the ions in solution. So we've got our +3 and our hydroxide. All right, so there's our equilibrium. Now we need to figure out if it actually does precipitate with the concentrations that we were given. So our KSP, we're going to use our equilibrium law. KSP is going to be the concentrations, the product of our concentrations of our products. It's a mouthful, I know. So we have iron and hydroxide. We just need to make sure we balance so that we don't forget that cube there. There's our equilibrium law. What are these concentrations? Now, here's another tricky bit. They're not the concentrations given in the question. Because what happened was these were mixed. So this was the concentration of iron chloride when it was in this volume. And this was the concentration of sodium hydroxide in this volume. But when they mix together, the total volume is going to be 125 milliliters plus that 425 milliliters, which is a total volume of 550 milliliters. So we've changed the volume that these ions are in. Therefore, we've changed their concentrations. So let's recalculate their concentrations. So first, for our iron. Okay, so these ones. Let's look up these ones. So initially we had iron inside of 125 milliliters. And it had a concentration of 1.5 times 10 to the minus 4 moles per liter. And that was inside of 125 milliliters. But then we changed it and we put it together inside of a total solution of 550 milliliters. So if we multiply by this ratio, we will get its new concentration inside of its new volume, which turns out to be 3.41 times 10 to the minus 5 moles per liter. Now we have to do the same thing for hydroxide. So initially, hydroxide had a concentration of 5.2 times 10 to the minus 3 moles per liter, and it was initially inside of a concentration of 425 milliliters. And then it was added to another concentration and therefore had a new volume of 550 milliliters. So again, multiplying by this ratio gives us our new concentration for hydroxide, which turns out to be 4.02 times 10 to the minus 3 moles per liter. All right, so now that we have our new concentrations, let's do a trial quotient. What would happen if we multiplied these concentrations in step with our equilibrium law? So iron, 3.41 times 10 to the minus 5, and hydroxide, 4.02 times 10 to the minus 3, and we're going to cube that. What we get is 2.2 times 10 to the minus 12. Now, the solubility product constant for iron hydroxide, you can look up on a table, and KSP is actually 2.6 times 10 to the minus 39. Oh my goodness. That means Q is much, much bigger than KSP. And if Q is much, much bigger than KSP, our concentrations are way higher than they need to be to get a precipitate. Therefore, oh yeah, we are definitely getting a precipitate. So precipitate is formed. Now our last question is a Le Chatelier's problem, where we look at the effects of changing conditions that alter equilibrium. Now, I recently created a complete tutorial on this because I know students, especially my students, really don't like this. So I'm just going to go over one problem here, but if you need more help on it, go check my full tutorial on it. So for each of the following, at this dotted line, that's where equilibrium is changing, state the change and the effect. All right, let's start with the first one. So with the first one, here's what I want you to notice. Something happened here, but only to this substance. Therefore, it was added. So N2O4 was added. Its concentration spiked. Okay, there's only three things that can happen. One, something is either added or removed. And in this case, you will get a spike for one substance. So spike, a single spike. Another option, you can have a temperature change. And when you change the temperature, everything gradually changes. You don't see any spikes, so no spike. Another thing that can change is the pressure. If you have a pressure change, you get a pressure change by changing the volume. When you change the volume, you change the concentrations of every gas inside of it. So everything spikes. So all spikes. So for our first example, only one thing spiked and it went up. So this was added. Now, if we add, N2O4 was a reactant. So if we add a reactant, we're going to get more of those reactants colliding, and therefore a forward reaction is going to be preferred. In our second case, well, look, spike, spike, spike. Everything spiked, therefore pressure. Okay. But here's the question. Did pressure increase or decrease? Now, if everything is spiking up, all their concentrations are increasing. To increase their concentrations, concentration, if you remember, is moles per volume. To increase concentration, you would have to decrease volume. So volume was therefore decreased. And if you decrease volume, pressure must have been increased. So we know that pressure was increased. How did this affect this reaction? Well, when pressure increases, all the molecules like to react to form the least number of molecules. All right. So if we count our moles, so here we have 2 moles on this side, and here we have 2 and 1, so a total of 3. So it's going to prefer a reverse reaction to the least number of molecules. All right, so that's it for that tutorial. I hope it helped. And if you need more practice, you can go check out the Le Chatelier's principle, and I will also soon be doing a live stream.